Professor Inauguration, the Acting Executive Dean, Faculty of Science, Professor Mallick, our inductee, warm word of welcome to you. I know it's a very special evening for you. Professor Muller, our respondent, also a professor in the Department of Chemistry at the University of Johannesburg, senior leaders of the university, members of Senate and other academics, distinguished guests, ladies and gentlemen, Sunny Bonani, goeienaand, good evening, Tobela. It's indeed a great honor and special privilege for me to welcome you to the Professorial Inaugural Lecture of Professor Mallick. As I do so, I wish to express a warm word of welcome to loved ones, colleagues, special guests, and other visitors. This is indeed a proud and joyful yet a landmark moment for all of you, for Professor Mallick, and of course for us here at UJ and higher education in South Africa and beyond. The inauguration of professors is a public ceremony in which newly appointed professors are inducted into office by the Vice-Chancellor and deliver their inaugural addresses. The ceremony has its roots in the medieval university and serves multiple purposes, and I'm going to highlight two of those purposes. Firstly, it's an expression of welcome and an entry for new professors, joining the circle of colleagues who are already professors. And secondly, it provides a platform for the professors to display their expertise in the discipline and showcase their research. Today we gather to be a witness to the entry of Professor Mallick to the illustrious community of scholars at the University of Johannesburg and other universities in the country. It is a celebration of the contribution to the discipline and ultimately the impact on society. Professors provide the university with its identity, character, and academic legitimacy and integrity. The inaugural lecture is a rite of passage, Professor Mallick, following the confirmation of the appointment of a professor. This evening, we will listen to Professor Mallick, as we say, as the gown goes to town. By this, I mean that the power of the inaugural address is when the expertise is showcased beyond the corridors of the university and reverberates within society. It stands out as a moment of pride for the incumbent, fellow scholars, the university, and ultimately society. For the German philosopher and diplomat Humboldt, a university referred to the whole community of scholars and students engaged in a common search for truth. Newman spoke about teaching universal knowledge. Recently, universities have been viewed as instrumentalist, serving the purpose of the economy or utilitarian in purpose. I would hope that we can break out of these narrow conceptualizations and reflect on the university as contributing to the public good. Edwards said in an article on defiance and taking positions, offers a formulation of the ideal role of the true intellectual, and I quote as follows: one who commands a vast knowledge of his/her discipline, who is rigorous in the analysis of literature, who views being an intellectual as a vocation, the intellectual who considers it's necessary to step into the public sphere and to speak truth to power, namely to question, interpret, and understand authority rather than consolidating it, to step out of the boundaries of the academy, to connect oneself, to affiliate oneself, to align oneself with an ongoing process or contest of some sort, perhaps with the aim of improving the lot of the oppressed. The intellectual who functions as a kind of public memory to recall what is forgotten or ignored, to make the connections that are otherwise hidden, and to provide alternatives for mistaken policies. No pressure on you tonight, clearly, when we look at that statement. It remains this for us as a university with a Pan-African vision to derive our mandate as intellectuals and as professors. And when we look at this mandate, ladies and gentlemen, we ask the question, how do we embrace the role of a professor as a disruptor while continuing to be a flagship carrier of our disciplines? This evening, we will listen to Professor Mallick as one further step in the journey of being a professor. This is a journey which does not culminate once this lecture has been given, Professor. It's a self-reflective pause in the journey of your route as a professor going forward, with a promise of more to enrich our minds and simultaneously contributing to the rich intellectual body of the work in the related discipline. Let me now invite the Acting Executive Dean, Professor Inauguration, to introduce our inductee. I thank you, Realabolga, Siyabonga, baie dankie.
Thank you, Professor Swart. Good evening, ladies and gentlemen, colleagues, Professor Mallick. Professor Kaushik Mallick obtained a BSc with honours in chemistry and from the Calcutta University and his MSc specialising in physical chemistry and PhD in chemistry from the Magdad University in India. Professor Mallick spent several years from 1999 to 2006 as a postdoctoral fellow at the Indian Institute of Technology at Kharagpur in India, the University of Witwatersrand, and the Korea Advanced Institute of Science and Technology. In 2007, he joined Mintech as a senior scientist. Professor Mallick was appointed as an academic staff member at the Department of Chemistry, University of Johannesburg in 2012, and promoted to a full professor in 2016. Professor Mallick teaches both undergraduate and postgraduate courses on physical chemistry and material sciences. Professor Mallick is a rated researcher in the C category, evaluated by the National Research Foundation in South Africa. His research is in the interdisciplinary field of material science, such as organic catalysis, electrochemical sensors, and various aspects of energy storage and harvesting systems. Professor Mallick recently also initiated a research program on materials science in computer applications, with special emphasis on resistive switching for random access memory and neuromorphic systems. He has published more than 100 research articles in various peer-reviewed journals and book chapters, with total citations of 2,775 and an H-index of 28. Professor Mallick also acts as editorial board member of Gaussian Physics, Scientific Reports from Nature Publishing Group, and Material Science of the Greater.
Dear colleagues and friends, thanks for your presence. The inaugural lecture is an opportunity for me to inform you about my research activities and my future research plans. The lecture will celebrate my journey along with my teachers, my students, and my collaborators, the way of some 20 years for seeking the Philosopher's Stone. The inaugural lecture is not easy, trust me. There is an expectation from the audience that as a professor, I have to present something which is professorial and intellectual, that can entertain or at least stimulate the audience with different knowledge background, that I will never likely to find the opportunity to deliver the lecture again in front of them. And finally, at the same time, I have to present something which is representative of my area of research expertise. Let me try to do that. The title of the topic of my presentation is the tailoring of functional materials for multidisciplinary research. Functional materials, the best definition I found from the Google, definitely, that the materials with superior and versatile properties. And these are the materials, they are called functional materials, that is alloys, semiconductor, polymer, and nanomaterials. When the polymer and nanomaterial combine with each other, they form the composite material, and the potential application of the composite materials are in the field of catalysis, synthetic organic chemistry, condensed matter physics, photonics, electronics, sensor, and energy application. Now, I will talk about the polymers with special emphasis on the conjugated polymers. These are the few examples of the conjugated polymers, among them polyaniline, and its derivatives have become the focus point of interest due to the environmental stability, controllable electrical conductivity, doping-dependent redox properties, and easy to synthesize and give different size and shape. Now, when nanomaterials combine with the polymers, they form the polymer nanocomposite and create the host polymer with interesting physical properties and potential applications. There are several methods you can use for make the metal polymer composite materials, but in situ polymerization and composite formation is the method we developed few years before in the year 2005, where metal salt and the monomer was the starting material. The choice of metal salt in such a way that it can oxidize the monomer, and during the oxidation process, the monomer forms polymer. And during the process, the electron released, and that electron reduced the metal salt and form the metals nanoparticle and ultimately form the metal polymer nanocomposite material. The metal polymer nanocomposite material have potential advantage in the area of synthetic material science because the polymer and the nanoparticle are produced simultaneously, and that cause an intimate contact between the particle and polymer through functionalization. The functionalization is very important parameter for the metal polymer composite material. These are the few examples of the metal polymer composite materials, that is with gold polyaniline, with copper polyaniline, derivative of copper polyaniline, and the palladium. And these are the nanoparticles. You can see the bright spots, these are the nanoparticles. Now, why the metallization of the polymer? What is the use of it? The resultant material would acquire the quality from both components, good stability and high conductivity from the metal, easy processing and lightweight from the polymer, and superior optical property from both the components. Now, why nanometallization? Why it should be not be a bulk one? Because the nanocrystal exhibit exceptional optical, magnetic, electrical, and catalytic properties which are different from the bulk. Now we did some nanocatalyzed synthetic organic chemistry. You can see that palladium polymer composite for the carbon-carbon bond formation reaction. We apply this material for Heck, Suzuki, and Sonagashira coupling reaction for the synthesis of natural products, pharmaceutical products, and fine chemicals. You can see that the dark spots, these are the palladium nanoparticle, and these are the reactions. We also do the transfer hydrogenation reaction for alpha beta unsaturated carbonyls. It is not always true that it forms the nanoparticle. Sometimes it happens, it gives the intermediate valency. Suppose if we start with the copper 2, it gives the copper 1. If we start with the palladium 2, it gives the palladium 1. You can see the some of the examples. Copper 1, formation of the copper 1, it started with the copper sulfate, the valency was copper 2. Similarly, it was palladium 1, it started with the palladium 2, K2PDCl4. Now this plus 1 valency with the polymer, where the polymer used as a ligand, also very important and catalytic application. You can see this material gives the good coupling between the terminal alkyne with aryl and vinyl halides. Palladium poly 3 aminoquinoline. It is called Sonagashira coupling. And here, copper polyaniline, by using the XPS study, we confirm the copper in the plus 1 state and copper catalyzed azide alkyne cycloaddition reaction. For this reaction, you can see that reaction takes place around 7 hours and 5 hours. But when the same reaction is performed under microwave condition, it gives 15 seconds. But the problem is you cannot recover the catalyst and use it for the further reaction. Because microwave reaction is a destructive condition, the catalyst becomes deactivated very soon. Now the electrical and magnetic property of the gold polymer composite material. So this is gold nanoparticles. These are the gold nanoparticles, and these are the polymer. This is the polyaniline again, and we measured the transport property of the material of the polyaniline alone and the gold polymer composite materials, and we found that due to the presence of gold nanoparticle, the conductivity characteristics of the polyaniline has changed near insulator to low charge carrier density semiconductor with the carrier concentration value of 0.88 into 10 to the power 15 per centimeter cube. We also did some magnetic study by using this material, and surprisingly we found at very low temperature it gives the paramagnetic property, where both gold, and we know that gold and polyaniline is diamagnetic in nature. So from where the paramagnetic property comes, we found that at low temperature the d orbital electron is pulled by this organic component and create a vacancy, and that create a paramagnetic property of the material. Cerium ammonium nitrate, a good oxidizing agent, and we use for polymerization reaction of the polyaniline, and we found that during the reaction cerium in the +4 state converted to +3 state, which is magnetic, which is highly paramagnetic, and gives the paramagnetic character of the polyaniline. Similarly, cerium sulfide, it gives the luminescence property and the magnetic property as well of this composite material. We also did some study for the proton coupled electron transfer reaction, that is hydrogen atom transfer reaction. It is popularly called as HAT reaction, and we found that this kind of reaction can also be catalyzed by the metal nanoparticles. These are the silver nanoparticles, and we found that this kind of reaction without nanoparticle, it needs 108 minutes, but in presence of nanoparticle it catalyzed, and for the completion of the reaction it needs only 17 minutes. So it indicates that the nanoparticle act as a catalyst for this kind of reaction, and this is our first kind of report where we showed that proton coupled electron transfer reaction can also be catalyzed by using metal nanoparticles. Now, generally, we categorize the reaction, we categorize the research in two segments broadly. One is the basic or fundamental, another is the applied research. Now, if you see in this picture that basic research is kind of knowledge discovery, whereas knowledge application is the applied research. But from basic research to applied research is called a death of valley. It's very difficult to do something and get some positive result in the laboratory and to carry over to the pilot plant. It is really difficult. You have to pass through a lot of steps: engineering development, prototype development, and technology deployment. But I can give you some examples where some basic research which had discovered 300 years before, but still now it is recently applied for various applications. The Newton's law of motion and theory of gravitation. Now, these days, maybe last 50 to 75 years before it is applied for aerodynamic system. The law and the theory was proposed or discovered by Newton, I think middle of 17th century. And recently, Albert Einstein published the general theory of relativity in 1916. But the Global Positioning System project was launched by the US Department of Defense in 1973 for the use by the United States military and become fully operational in 1995. So these are the basic research at that time. Now it becomes knowledge, it was knowledge-based research, now it is applied research, which I call it knowledge application after long years interval. Now these are some of the product of applied research during 18th century. You can see the spinning machine, coke-powered blast furnace, textile machines, and the most important technology is the steam engine. This is during the 17th century, the beginning of the first industrial revolution. The first industrial revolution emergence of mechanization, that is coal-driven steam engine, a new type of energy. You can see this train. This is from my village. And it is in the year 1985, the last locomotive engine, steam engine, now it is stopped. And you can see the first human-driven pollution created officially at that time, at the middle of during the first industrial revolution. Now, the second industrial revolution, emergence of another source of energy, that is electricity, gas, and oil. And you can see the pollution created due to that one. Now, the third industrial revolution, emergence of the nuclear energy, and also the rise of telecommunication and computers. But the world electricity production by source, this is the diagram. In 2016, we are still dependent on the coal, 40%, 23% for the fossil gas, 17% of the hydroelectricity, and only 10% of the nuclear energy. Still we are dependent on the fossil fuel, and still we are generating carbon dioxide for the global warming, and that is caused the global warming. Now this is the graphical representation how much carbon dioxide we are generating every year. This is the carbon dioxide parts per million, and you can see the x-axis is the year, and y-axis is the parts per million carbon dioxide. In the year 2005, it is around 380 parts per million carbon dioxide. In the year approximately 2020, it is more than 400 parts per million carbon dioxide. The seasonal cycles related to the seasonal vibration due to the photosynthesis, you can see this type of graphs. These are the photosynthesis effect. And the long-term trend is related to the addition of carbon dioxide to the atmosphere through the combustion of the fossil fuels. Now, what is the consequence? Climate change and global warming. The melting of the polar ice caps. The rising the sea water level and the coastal flooding. So these are the consequences. Now, Industrial Revolution 4. So in the first, second, and third industrial revolution, we have generated a lot of carbon dioxide and methane gas, because hydroelectricity is produce a lot of methane gas from the reservoir. And methane is more powerful than carbon dioxide for global warming. Now, Industrial 4, one of the main effects of the fourth industrial revolution is the increase of productivity, supported by the digital economy, using the technologies of artificial intelligence, robotics, IoT, biotechnology, and nanotechnology. IoT means Internet of Things. And it is characterized by the speed, intelligence, and efficiency. How speed your computer, how intelligent is your robot, and how efficient is your technology. For the enhancement of professionalism. Now, if you consider all of these are for whom? These things are for the us, human being. This is of the people, by the people, for the people. Now, what is the consequence of the fourth industrial revolution? Electronic trash. Now, estimated electronic trash in the world is 44.7 million ton. And the electronic trash are the computers, fax machine, printers, tablets, smartphones, and ever expanding numbers. Smartphones. We are buying one today. The next day, another model comes. We buy another one. And we don't know what will happen before one. Each individual of South Africa generates about 6.2 kilo per annum of e-waste. And the Department of Environment Affairs estimate an annual deposit of 360,000 tons of e-waste every year in South Africa. The DESCO, a Johannesburg-based plant specialist in e-waste, they think e-waste is not seen as a threat. Another organization, California Department of Resources and Recycling and Recovery, e-waste is much more complicated. It cannot be easily handled. And this data, I found it from this person. I think she is also our student at UJ. It was published in Mail and Guardian. The South Africans are drowning in e-waste. During the first industrial revolution, second industrial revolution, and third industrial revolution, we are concerned about the molecular carbon dioxide or methane. Now, during the fourth industrial revolution, we are concerned about the elemental carbon. We already achieved 3 Nobel Prize for the discovering the buckyball, carbon nanotube, and graphene. And they act as a silica, as poisonous as silica, which is responsible for the disease silicosis. And during the fourth industrial revolution, where the nanotechnology is concerned, all the elements, either oxides or the sulfides or the quantum dots we are producing, we don't know where we are using them and how to dispose them. And all the periodic tables are involved. And the e-waste, the effects on human, the damage of the central and peripheral nervous system, blood system and kidney, effects on the brain development of the children, and etc., etc. But these are the negative side of the fourth industrial revolution. There are a lot of positive side of the fourth industrial revolution. This can be easily tackled if the government is properly legislate. The producers, if the producers properly tell what type of material are used for this purpose, then it can be easily handled. The fourth industrial revolution, this is a revolution. You cannot stop it. It will go like the first industrial revolution, the second industrial revolution. It is a process. You have to have, whether you agree it or you don't agree it, you have to accept it. It is the process of human development. And fourth industrial revolution, our knowledge is not that too much, because we do not see the whole picture. It is like the elephant. What an elephant look like, and we are the blind person. We touch the leg and we think it is a tree. We touch the tail, we think it is a rope. We touch the ear, we think it is a fan. But as a whole, it is a beautiful animal. So fourth industrial revolution, if you want to see the positive sides of the fourth industrial revolution, you can see. I mentioned previously, using the technology, artificial intelligence, Internet of Things and robotics. You can use it for the smart banking system, and that impact on the economy and the fraud prevention. You can use it for the education system. Education system, not the university education system. In the education system, primary, secondary, health education, environmental education, for different kind of education system. By using the nanotechnology, I also mentioned, using the nanotechnology, you can use the drug delivery and biosensor that have an impact on the healthcare system. Biotechnology is the gene therapy. It is also have an impact on the healthcare system. Renewable energy is one kind of green energy where you can use the solar power, wind power, different kind of things. Even the surrounding vibration, piezoelectric effect, and that impact on the environment. So if we can honestly utilize the fourth industrial revolution or apply the fourth industrial revolution, we can get rid of the carbon-based pollution. Nanotechnology is the another perfect memory and data storage. In our group, we are producing the memory and data storage material by using the nanotechnology devices. And this memory and data storage also supplement the artificial intelligence, IoT, and robotic system. So it is a huge thing. It is a process of the development. In the first industrial revolution, it was the epicenter was the Europe. The second and third industrial revolution, the epicenter was the USA. Fourth industrial revolution, you have to accept it, the epicenter is in China. Now, let me explain what I am doing in my group based on the fourth industrial revolution. Electrochemistry and biosensor application. These are the biomolecules, neurotransmitter. We are sensing the neurotransmitter and try to digitalize the neurotransmitter application. Even the glucose, we use the digitalized kits for the detection of glucose. We also do some fuel cell application by using methanol as a fuel, and it liberates the hydrogen energy, hydrogen as an energy. It is a non-polluting energy source. We also do the organic reactions, simple organic reactions, by using the light energy, that is daylight energy, and a quantum dots. And due to the daylight energy, we have to, we do not use any toxic chemicals like base, very toxic. We can remove the base. This electron can be used for extract the proton from the reaction. Ultrafine bismuth oxide for the storage application. So this is the bismuth oxide nanoparticles. This is the TM image, and we use this material for the energy storage application. You can see the specific capacitance of this material is 407 Faraday per gram, and energy density is 113 watt hour per kg at 1 ampere per gram. And the same material can be used as a data storage. And you can see the device demonstrated write, read, and erase response using the different pulse. And this is the endurance study, that is storing and processing the data 0 and 1 in a binary fashion. And this is the non-volatile study. So capacity of the storing the data in absence of the power supply of the device under test. Similarly, we are using the polyaniline stabilized copper nanoparticles as a memory storage application. This is the IV curve. This is the endurance state of the device for 10 to the power 3 cycle. This is the condition applied for the endurance state, and this is the condition applied for the non-volatile behavior of the device. And this is the mechanism of the reaction, that is, and we propose that on state is followed by the ohmic behavior, whereas the off state is dominated by the Poly-Franklin emission. And this is the mechanism as plain schematic diagram where the electron flows from which direction to which direction. So these are the infrastructural facility I have in my laboratory. This is the non-volatile memory and neuromorphic workstation. This is the simple electrochemical workstation. This is the dielectric measurement system. This is the ferroelectric loop stretcher. We are also doing some work on the ferroelectric and dielectric material for the energy storage and energy harvesting application. This is the cryogenic system. This is the piezoelectric instrument. And we are also doing some lithium-ion battery work. And this is the components for the lithium-ion battery. This is the globe box, and this is a photochemical workstation. Now, I also have a lot of responsibility in teaching and learning. And my teaching philosophy, I try to follow. A mediocre teacher tells, the good teacher explains, the superior teacher demonstrates, and the great teacher inspires. And this teaching philosophy inspires me to improve every day. I have a teaching responsibility. I teach the physical chemistry in the 3rd year. And when I came to joined in this university, I changed some syllabus, but in the theory, but I changed a whole lot of practical syllabus. I introduced the most recent and application-oriented practical syllabus that can link between the theory and the practical syllabus. For my research students, particularly master's, PhD, and postdoctoral students, as they are coming from the different diverse area, my students has the engineering background, they have the physics background, and they also definitely have the chemistry background. And they need the rigorous coursework to learn chemistry, to learn physics, to learn engineering, to learn device fabrication, etc. Now, before doing the concluding remark, let me see what happened during the last 45 minutes during my lecture time in the world. 3.1 10 to the power 7 liter of fossil fuel are used during the last 45 minutes. This amount of tons ice melt in the Antarctica. This amount tons of garbage are generated in this planet. This amount of smartphones are dumped. 5,085 children are born under poverty. 7 plant or animal species disappeared from the earth. So I want to conclude my lecture that as a scientist, it is my moral duty to make this planet habitable for the next generation. Thank you.
Ladies and gentlemen, namaste. I have come to know Professor Mallick over the past few years, and today I'm able to summarize the experience in 2 words: brutally honest. I mean, if you look at the lecture, who else would compare the 4th Industrial Revolution to a blind man and an elephant? I also dare you after the event to go and ask Prof Mallick anything you want, and you might get a brutally honest answer. The problem with the brutally honest answer is it's not the answer that you wanted. But eventually and later on, you will realize that this is the best answer at that stage in your life. Prof Mallick touched a lot on the Industrial Revolution, and if you look at the Industrial Revolution, more particularly what is a revolution, it is a huge change in society. And people don't want to change. A society does not want to change. So a revolution will never happen if a society does not want to change. What we need is revolutionists. And if you look at the definition of a revolutionist, it's a person that doesn't sit around all day. He goes out there and he wants to do things to change the world. And tonight I want to designate Professor Mallick as a revolutionist for the 4th Industrial Revolution. Now, Professor Mallick might be sitting here and he doesn't feel like a revolutionist. But if you go back into history, and I've taken the liberty to do that, and I've looked at the Indian history, specifically in the time under the British colonial rule, people were not happy, but they did not really want to change, because it's hard to change. And they needed revolutionists. And there were 4 people, and I cannot remember all the Indian names, unfortunately. But the 4th person there was Shailendra Mallick as well. And Shailendra Mallick is remembered by the Indian community as he was bestowed the title of Raja Shailendra Mallick eventually. So, ladies and gentlemen, I think we might have a reincarnation amongst our midst of the very first Indian person. I want to conclude with just by coming back to the definition of a revolution, and I want to address this to UJ itself. It's a significant change in society. And what Prof Mallick doing now, he's doing in his laboratory. And his laboratory is not the society. It needs to change. It needs to get out there. And the sooner we put forth the research that he is doing out there, the more easy it will be to accept the 4th Industrial Revolution. Prof Mallick, I want to thank you, and I wish you the best on your journey as that guy. Thank you.
So, ladies and gentlemen, you would have seen that our colleague, before he gave his address, he was quite underdressed for the occasion. And I'm not talking he's not wearing a tie, talking the rest of us were wearing gowns, and he came in without a gown. So traditionally, is we listen to the inductee. It's like a judgment call. He's got to prove himself. And I see he had lots of time to practice because he's already been a full professor from 2016. But I think you would agree with me that following what his presentation here tonight, he really deserves for us to robe him now and induct him as a full professor. Please join me in front here. Let's put a gown on. I'm going to ask the two colleagues from the faculty to assist him. No? Professor Mallick, ladies and gentlemen. So I think our respondent has summarized it very nicely for us. I'm not talking being a revolutionary. I'm talking about the content that's being displayed for us. Because I think the one thing that you've touched on, Professor Mallick, is that although we're talking about high-level research and the transition from research, just from the basic research to the applied side, that we can use it in society, that resonates with the parts that I've highlighted in my speech. But I really liked what you touched on, is that as much as we talk about the fourth industrial revolution, we sit with a real challenge, not just in South Africa, worldwide. The number of children that's still born in poverty, the collapse of the polis, range of other issues. And I really said, that really found me in your presentation. Because I think it's so easy for us to get fixated on the fourth industrial revolution without really contextualizing with real life out there. And the aspects that you've highlighted for us talks to the real life. And I'm not just talking about the number of kids born in poverty. I'm talking about when you spoke about the e-waste, where we've got some of the best legislation in Gauteng. I'm not saying it's the best legislation because I was part of the founding committee of those legislation. But the challenges we have in applying our legislation. And as we sit here tonight, ladies and gentlemen, many of you would have seen the reports of the high level of pollution in Van der Bijl Park, in Sasol-related environments, in Pretoria. A colleague of mine works for the MRC, where she does work on lead in the environment. That in many societies, lead in the environment is 300 times higher than the WHO minimum guideline document. And I think the way you've contextualized that for us to use the research to enhance society, but also contextualizing it in the real life aspects that we're facing nationally, continentally, internationally, with the real challenges out there. Thank you very much for sharing that for us. We really do appreciate it. Let's give him another round of applause, ladies and gentlemen. And Professor Muller, for being brutally honest, it was a honest rendition of the talk, summarizing really the key factors for us. It's much, much appreciated. Thank you very much. And then also allow me to thank the colleagues and leadership in the faculty for creating environments for people to grow, to develop, to do work that's really related for what we need, not just in South Africa, but for broader society. It is much appreciated. Ladies and gentlemen, there will be refreshments available on my right-hand side. I think most of you know where it will be served. Many of you have been there before we started. But just also to highlight that our inductee, Professor Mallick, would be at the door for a congratulatory handshake from your side. He will be available there. And may I please ask you to stand as the procession leave the venue. Thank you very much for your attendance. Much appreciated.